In this episode, we're going to focus on what it really means to protect data while it is moving from one place to another, because a surprising number of security failures happen not because data was poorly stored, but because it was exposed during travel. When beginners picture a breach, they often imagine someone stealing a database or breaking into a server, yet everyday systems constantly move data between browsers and websites, phones and applications, services, and users and cloud resources. Anytime data is in motion, it can be observed, altered, redirected, or replayed if the path is not protected. The main tool we rely on for protecting most modern internet communication is Transport Layer Security, TLS, which is the technology behind the familiar idea of a secure connection. That secure connection is not just about secrecy, because it also helps you know who you are talking to and whether the information was changed along the way. By the end, you should be able to describe what TLS is doing in plain language, why certificates are central to trust, and how certificate hygiene prevents avoidable outages and security gaps. A helpful first step is to define what data in transit actually means, because it is easy to confuse it with data stored in a system. Data in transit is any information being sent across a network, whether that network is the public internet, a private company network, a wireless connection, or even a communication path inside a cloud environment. When you load a web page, sign into an account, submit a form, or an application calls an internal service, you are sending data in transit. The risks include eavesdropping, where someone reads the data, tampering, where someone modifies the data, and impersonation, where someone tricks you into talking to the wrong destination. In the physical world, it is like sending a letter that might be opened, edited, or redirected while it is traveling through the mail. If you want a secure system, it is not enough to lock your filing cabinet, because you also need to protect what you are mailing between offices. Once you see that most modern systems are basically constant conversations, you understand why transit protection is a core security requirement, not a special feature. Now we can talk about what TLS actually provides, because the common beginner summary that it encrypts traffic is true but incomplete. TLS aims to provide confidentiality, integrity, and authentication for a connection. Confidentiality means that someone who sees the traffic cannot read it, because it is encrypted. Integrity means that if someone tries to change the traffic, the receiver can detect the change. Authentication means that the client, like a browser or application, can verify that it is connecting to the correct server, not an imposter. This trio matters because an attacker does not always need to read your data to cause harm. Sometimes they only need to change it, like altering a payment destination or injecting malicious content. Also, if you are tricked into connecting to the wrong server, encryption alone does not save you, because you might be securely sending secrets to the attacker. TLS is designed to prevent that by using certificates that connect a domain name or service identity to a cryptographic key, allowing clients to verify who they are talking to. To understand how that verification works, you need a simple mental model of certificates and the trust system behind them. A certificate is a digital document that binds a public key to an identity, such as a domain name, and it is signed by a trusted authority. The trusted authority is typically a certificate authority, CA, which is an organization whose job is to validate identities and sign certificates so others can trust them. Your computer or phone has a set of trusted CA certificates already installed, called a trust store, which is why your browser can automatically decide whether a site's certificate should be trusted. When you connect to a secure site, the site presents a certificate, and your device checks whether that certificate chains back to a trusted CA and whether it is valid for the name you intended to reach. If the checks pass, your device is willing to proceed with a secure handshake and build encryption keys for that session. If the checks fail, you often see a warning, because the system cannot be confident about who is on the other end. This is the heart of certificate hygiene, keeping that identity evidence correct, current, and trustworthy. The handshake is the next concept to grasp, because it explains why TLS is not just a simple on and off switch. During a handshake, the client and server agree on how to secure the connection, including which cryptographic algorithms to use, and they establish shared secrets for encryption. The handshake is also where the server proves it controls the private key associated with its certificate, which helps ensure that the server is not just presenting someone else's certificate. Modern versions of TLS are designed to negotiate secure settings and to support forward secrecy, meaning that even if a long-term key is compromised later, past conversations remain protected. Beginners do not need to memorize the math, but they should appreciate that the handshake is a negotiation, and negotiation creates choices. Those choices can be strong or weak depending on what versions and algorithms are allowed. This is why the title mentions TLS choices, because allowing outdated versions or weak options can undermine the entire point of using TLS. TLS choices usually come down to version support and cipher suite configuration, and it is important to understand what those words mean at a high level. A version refers to the specific standard of TLS being used, and newer versions fix weaknesses and simplify secure behavior. Older versions may have known issues or allow unsafe options, which is why security programs eventually deprecate them. Cipher suites are combinations of algorithms that handle key exchange, encryption, and integrity, and the exact set offered by a server influences what clients might end up using. If a server offers weak suites for compatibility, a client might choose them, especially if the client is old or misconfigured. That compatibility temptation is one of the biggest reasons weak settings linger. A security-minded approach is to prefer modern versions, restrict to strong cipher suites, and intentionally remove older options when they are no longer needed. The goal is not to make communication exotic. It is to make it reliably safe with the simplest, strongest default settings. Certificate hygiene becomes critical because even a well-configured TLS system fails if certificates are mishandled, and certificate mistakes are painfully common. Certificates have expiration dates, and if a certificate expires, clients will reject the connection, which can cause outages that look like sudden system failure. Certificates also must match the identity they claim to represent, such as a specific domain name. And if the name does not match, clients may warn or block the connection. Certificates can also be revoked if they are compromised, and revocation is a way of telling clients that a certificate should no longer be trusted. Hygiene includes tracking where certificates are used, renewing them before they expire, replacing them if keys might be exposed, and ensuring proper validation paths. In real systems, certificate hygiene is not just a security task, it is a reliability task, because expired or misconfigured certificates can bring down services as effectively as a hardware failure. This is why leaders care about certificate inventories, renewal automation, and clear ownership, because you cannot maintain what you cannot find. A common misconception is that once you have TLS enabled, you are fully protected in transit, but there are several ways transit protection can be weakened without obvious signs. One example is failing to enforce secure connections, where a system still allows unencrypted traffic as an option. Another example is accepting invalid certificates, which can happen if someone disables certificate verification to make a problem go away during testing and then forgets to re-enable it. There is also the risk of trusting the wrong certificate authority, such as installing extra trust routes that allow interception. In some environments, internal systems use self-signed certificates, which means they are not signed by a widely trusted CA, and that can be safe only if trust is managed carefully. If the trust configuration is sloppy, self-signed setups can lead to people ignoring warnings and accepting risky connections. The lesson for beginners is that transit security is not just about encryption existing. It is about correct verification and strong, enforced defaults. Another important idea is understanding where TLS sits in a system, because data might travel through multiple connections, and each connection is its own transit risk. For example, a user might connect securely to a front-end service, but then that service might connect to a back-end system without transit protection. In that case, the user's connection looks secure, but the internal link is exposed. This is why you sometimes hear the phrase end-to-end, which means protection is maintained across the full path. In complex cloud environments, services talk to each other constantly, and those internal conversations can carry sensitive data, credentials, or control messages. Leaders push for encrypting those internal links because attackers often move laterally inside environments once they gain a foothold. If internal service-to-service traffic is unprotected, an attacker who reaches the internal network can observe or tamper with valuable flows. Protecting data in transit must therefore be applied consistently, not just at the outer edge where browsers connect. Certificate hygiene also includes key hygiene, because certificates are tied to private keys, and the private key is what must remain secret. If someone obtains the private key, they may be able to impersonate the service or decrypt traffic in certain scenarios. Protecting private keys involves limiting who can access them, storing them in secure locations, and rotating them when there is reason to believe they might be exposed. Rotation means replacing the key and issuing a new certificate, which reduces the time window in which a stolen key remains useful. Hygiene also involves avoiding key reuse across many services, because shared keys create shared failure. If one service is compromised and its key is reused elsewhere, the incident spreads. A beginner does not need to manage keys directly to understand the principle. Keys are like master keys to a building, and the fewer copies and the tighter the custody, the safer everyone is. When key management is treated casually, TLS becomes a thin coat of paint over a deeper trust problem. A practical way to think about certificate hygiene at scale is to imagine a city where every building's door lock expires on a date, and you must replace locks before they stop working. If you do not have a list of buildings and their expiration dates, you will only learn about failures when people cannot get in, which is a terrible way to run a city. In the same way, organizations need an inventory of certificates and where they are deployed, along with the dates they expire and the authorities that issued them. Ownership matters because someone must be responsible for renewal and replacement, and that responsibility must be clear. Automation matters because manual renewal is error-prone and does not scale, especially when environments use many services. Monitoring matters because you want early warning well before expiration, not a sudden outage at the worst possible moment. All of this may sound like operations, and it is, but security and operations overlap heavily here because the trust layer of the internet is both a security dependency and a reliability dependency. It is also worth discussing the balance between compatibility and security because leaders often have to make decisions about which clients and systems must be supported. Some older devices or software may not support modern TLS settings, and keeping them working can tempt teams to enable weak versions or cipher suites. That decision increases risk for everyone, not just for the old system. A more disciplined approach is to treat outdated client support as a known risk that must be managed, possibly by isolating it, reducing its privileges, or planning for replacement. Even for beginners, the lesson is that security is often about choosing where you will accept limits. If you try to support everything forever, you end up supporting known weaknesses forever. If you cut off everything old instantly, you might break critical business processes. Good risk management is making those trade-offs consciously and documenting them rather than letting them happen by accident. As we bring these ideas together, the central story is that protecting data in transit depends on both strong TLS configuration and healthy certificate practices, and neither one can carry the full burden alone. Strong TLS choices mean using modern versions, restricting weak options, and enforcing secure connections so traffic cannot quietly downgrade to unsafe paths. Certificate hygiene means ensuring identities are proven correctly through valid certificates, that certificates are renewed and rotated before they fail, and that private keys are protected like the valuable secrets they are. It also means resisting the habit of bypassing validation when something is inconvenient, because bypassing validation removes the authentication part of TLS, which is what prevents impersonation. When these practices are consistent, transit protection becomes reliable, which reduces both security incidents and disruptive outages. When these practices are sloppy, transit protection becomes fragile, and the system fails either through exposure or through sudden loss of trust. The leadership mindset is to treat TLS and certificates as foundational infrastructure, not optional features, because every secure system is built on the assumption that communication can be trusted.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.